capacitor connected in series arrangement. Let us consider three capacitor has a capacitance C1, another capacitor has a capacitance C2, another capacitor has a capacitance C3 connected in series across a potential difference provided by the battery V. So, potential difference provided by the battery across the series combination of capacitors connected in series. Charge on each plate remains constant Q, Q, Q. But the potential difference between two plates of a parallel plate capacitor is different. V1, V2, V3 are the potential difference across the three capacitors. So, Q is constant. But what is the total applied potential difference across the series combination? V is equal to V1 plus V2 plus V3. Then V1 is equal to Q divided by C1, V2 is equal to Q divided by C2, V3 is equal to Q divided by C3. Then V is equal to V1 value Q divided by C1 plus V2 value Q divided by C2, V3 value Q divided by C3. Then V is the total potential difference across the series combination, which is equal to Q divided by CS. CS is the effective capacitance connected in series combination, which is equal to Q taken out commonly 1 divided by C1 plus 1 divided by C2 plus 1 divided by C3. Q get cancelled. 1 divided by CS is equal to 1 by C1 plus 1 by C2 plus 1 by C3. So, this expression is the reciprocal of effective capacitance connected in series combination, which is equal to sum of its reciprocal of the capacitance of individual capacitors. So, very important one. If capacitors connected in series, charge on each capacitor remains constant, but the potential difference across each capacitor is different. So, reciprocal of effective capacitance 1 divided by CS is equal to 1 by C1 plus 1 by C2 plus 1 by C3. So, here there are two capacitors has a different capacitance C1, C2 connected in series across the potential difference V. So, charge on each capacitor remains constant, but the potential difference across the two capacitors V1 and V2. Then ratio of charge on the two capacitor Q is 1:1 because charge on the each capacitor remains constant. The ratio of charge on the two capacitor is 1:1. Then what is the ratio of potential difference between the two capacitors? Generally C is equal to Q by V, V is equal to Q by C. Then potential difference across the first capacitor V1 is equal to Q divided by C1. Potential difference across the second capacitor V2 is equal to Q divided by C2. Equation number 2. Then we are in our aim to calculate the ratio of potential difference across the two capacitor V1 divided by V2 is equal to Q divided by C1 into C2 divided by Q. Get cancelled. V1 divided by V2 is equal to C2 divided by C1. It is another important expression. Ratio of potential difference between two plates of a parallel plate capacitor in series combination, which is equal to C2 divided by C1. Then capacitors connected in parallel. Capacitors in parallel. There are three capacitors as a different capacitance C1. Another capacitor has a capacitance C2. Another capacitor has a capacitance C3 connected in parallel combination across the potential difference V. So if three capacitors connected in parallel across a potential difference provided by the battery V, potential difference across each capacitor remains constant, which is equal to battery potential difference, which is equal to V. But charge on the three capacitor is different. Charge on the first capacitor Q1, charge on the second capacitor Q2, charge on the third capacitor is Q3. Then what is the total charge provided by the battery to this parallel combination? Q is equal to Q1 plus Q2 plus Q3. So this is equation number 1. What is the charge on the first capacitor? Generally, Q is equal to CV. Q1 is equal to C1 into V, because potential difference between two plates of a parallel plate capacitor across the parallel combination remains constant. Equation number 2. Charge on the second capacitor Q2 is equal to C2 into V. Equation number 3. Charge on the third capacitor Q3 is equal to C3 into V. Equation number 4. Equation 2, equation 3, equation 4 substitute in equation 1. A total charge provided by the battery in parallel combination Q is equal to C1V plus C2V plus C3V. Then Q is equal to, we take common out V, C1 plus C2 plus C3. Then total charge supplied by the battery to this parallel combination, which is equivalent to Q is equal to Cp into V. So therefore substitute here Cp into V, which is equal to V, C1 plus C2 plus C3. V will cancel. Cp, which is equal to C1 plus C2 plus C3. So here effective capacitance connected in parallel combination, which is equal to sum of its capacitance of individual capacitors. Here ratio of potential difference across the parallel plate capacitor, which is equal to 1:1. Take two capacitor as a capacitance, difference capacitance C1 and C2 connected in parallel across the potential difference V. Charge on the first plate Q1, charge on the second plate Q2, potential difference between the two plates VV. Ratio of potential difference between the two plates of a parallel plate capacitor is same, that's 1:1. But what is the ratio of a charge on the two plates? Q1 is equal to C1V, Q2 is equal to C2V. Then ratio VV get cancelled. Q1 divided by Q2 is equal to C1 divided by C2. It is an important expression. If two capacitors connected in parallel, ratio of the charge on the two capacitors is equal to C1 divided by C2. Now we are going to see another topic in electrostatics lesson, especially in related to capacitor, energy stored in a capacitor. Let us consider uncharged parallel plate capacitor. X plate, Y plate, distance of separation between the two plates D, area of the each plate AA. Now battery is connected across the two plates of a parallel plate capacitor provided by the potential difference. Charge acquired by the X plate plus Q. Charge acquired by the Y plate is equal amount minus Q. Then space between the two plates is filled with an R medium. Electric field is established. The uniform electric field is established in between the two plates. Then developing the potential difference between the two plates of a parallel plate capacitor V, which is equal to battery potential difference. Then the parallel plate capacitor is completely charged. How much amount of work is done by a battery to store the electric charge Q on the parallel plate capacitor is stored in the form of electrostatic potential energy. U is equal to half CV square, which is equal to Q square divided by 2C, which is equal to half QV. This is the very important expression to associated with the capacitor, energy stored in a parallel plate capacitor, especially that space between the two plates is completely filled with an R. U is equal to half CV square is equal to Q square divided by 2C, which is equal to half QV. Then energy stored per unit volume of space between the two plates is nothing but energy density. So energy density which is equal to energy stored per unit volume of the space between the two plates in electric field, which is equal to of epsilon naught E square, which is equal to of epsilon naught E value V divided by D whole square, which is equal to of epsilon naught V square divided by D square. So is the energy density or electrostatic potential energy stored per unit volume of space between the two plates of a parallel plate capacitor is energy density of epsilon naught E square. Then the entire space is filled within a medium of dielectric constant. Dielectric constant epsilon naught, then energy density U divided by V, which is equal to of epsilon E square. So U divided by V, which is equal to of epsilon naught E square is the energy density. Means energy stored in between the two plates of a parallel plate capacitor per unit volume of the space within a medium is equal to of epsilon naught E square. We move to see another topic, sharing of charges in capacitors. Let us consider one capacitor has a capacitance C1. Then the capacitor is charged by a potential difference provided by the battery V1. Due to the potential difference V1, charge on the C1 capacitance is Q1. The next, another one uncharged capacitor has a capacitance C2, is charged by a potential difference V2. Due to the potential difference V2, charge on the second capacitor Q2. Now, both the capacitor is disconnected from the battery. So first capacitor has a capacitance C1, charge on the capacitor Q1, potential difference between the two plates of a parallel plate capacitor V1. Then second capacitor has a capacitance C2, charge on the second plate Q2, potential difference between two plates of a parallel plate capacitor V2. Now, positive plate of one of the capacitor is connected with the positive plate of the another capacitor, negative plate of the one of the capacitor is connected to the negative plate of the another capacitor, form the combination. Capacitance C2, charge on the capacitor Q2, then potential difference between two plates of a parallel plate capacitor V2. Then both the capacitor is connected, positive plate connected with positive plates, negative plate is connected with the negative plate of the other capacitor. Then charge distribution takes place until potential becomes equal. Then after distribution of charges, then both the capacitor is attains the same potential difference. That is called common potential V common, which is equal to total charge divided by total capacitance. So after distribution of charges, both the capacitor attains the same potential, then distribution of charges takes place. Then common potential, which is equal to total charge, means charge on the first capacitor, charge on the second capacitor. Q1 plus Q2 divided by total capacitance C1 plus C2. It is very important expression. If two charged capacitor with the different potential, with the different charges connected, positive plate with the positive plate, negative plate with the negative plate, so distribution of charges takes place until potential difference between the two plates of the parallel plate capacitor remains same, attains a common potential is equal to total charge divided by total capacitance. So V common, which is equal to Q1 plus Q2 divided by C1 plus C2, equation number 1. Already we know that charge on the first parallel plate capacitor Q1 is equal to C1 into V1. Then charge on the second parallel plate capacitor Q2 is equal to C2 into V2. Substitute in this equation. So common potential is equal to C1 V1 plus C2 V2 divided by C1 plus C2. It is another important expression. Common potential in this combination. So during the distribution of charges through the conducting wire until potential becomes equal, certain part amount of energy is dissipated in the form of heat in the conducting wire. Then how much amount of heat is dissipated in the conducting wire, that is heat lost or energy lost, H. Energy lost in the conducting wire due to distribution of charges in the conducting wire, which is equal to of C1 C2 divided by C1 plus C2 into V1 minus V2 whole square. Next, in sharing of charges in a capacitors, if both the capacitor has a different capacitance charged with the different potential is connected in the form, positive plate is connected with the positive plate and negative plate is connected with the negative plate, common potential across the two capacitors is equal to C1 V1 plus C2 V2 divided by C1 plus C2. During the distribution of charges, charge is flows through a conducting wire, certain amount of energy is dissipated in the form of heat is equal to half C1 C2 divided by C1 plus C2 V1 minus V2. So after distribution of charges, what is the final charge of the first capacitor Q1 prime? Then what is the final charge of the second capacitor Q2 prime? So final charge of the first capacitor C1, it's a Q1 prime which is equal to, generally Q is equal to CV. Q1 prime which is equal to first capacitor as a capacitance C1, V is the common potential after distribution, both the capacitor attains a common potential V common. So final charge of the first capacitor Q1 prime which is equal to C1, common potential total charge Q1 plus Q2 divided by total capacitance C1 plus C2. This is equation number 1. After distribution, both the capacitor attains a same potential difference. Final charge on the second capacitor Q2 prime which is equal to C2 into V common. Then Q2 prime which is equal to C2 into common potential total charge Q1 plus Q2 divided by total capacitance C1 plus C2, which is equivalent to C2 into common potential, another expression C1 V1 plus C2 V2 divided by C1 plus C2. Then final charge on the first capacitor which is equal to C1, common potential, another expression C1 V1 plus C2 V2 divided by C1 plus C2. The next another one special case. Case 2. Now there are two capacitors as a different capacitance C1 and C2 charged with the different potential difference V1 and V2. Positive plate, negative plate, positive plate, negative plate. Charge on the first capacitor Q1, charge on the second capacitor Q2 with charge with the different potential difference. Now, positive plate of the one of the capacitor is connected with the negative plate. Negative plate of the first capacitor is connected with the positive plate. Capacitance C1, potential difference V1, charge on the first plate Q1. Then second capacitor has a capacitance C2, charge with the potential difference V2, charge on the second capacitor Q2, but positive plate of the first capacitor is connected with the negative plate of the second capacitor, negative plate of the first capacitor is connected with the positive plate of the second capacitor. Then only redistribution of charges takes place in the conducting wire until both the capacitor attains a common potential. In this case, common potential V common, which is equal to total charge divided by total capacitance. So total charge Q1 plus, if the polarity of the capacitor is connected in opposite, one of the charge is taken as negative, minus Q2 divided by total capacitance C1 plus C2, then Q1 minus Q2 divided by C1 plus C2. It's a common potential. Then distribution of charges takes place until both the capacitor attains the same potential or common potential. V common is equal to Q1 minus Q2 divided by C1 plus C2. This formula is applicable if both the capacitor has a different capacitance, charged with the different potential, is connected with the opposite polarity, possess a same potential. V common is equal to Q1 minus Q2 divided by C1 plus C2, which is equivalent to Q1 value C1 V1 minus Q2 value C2 V2 divided by C1 plus C2. After distribution, both the capacitors attain a common potential. Final charge on the first capacitor Q1 prime, final charge of the second capacitor Q2 prime. How to calculate the final charge? Q1 prime, which is equal to C1 into V common. So Q1 prime, which is equal to C1, common potential in this case Q1 minus Q2 divided by C1 plus C2, which is equivalent to C1 into C1 V1 minus C2 V2 divided by C1 plus C2. Final charge of the second capacitor Q2 prime, which is equal to C2 into common potential, is equal to C2 of Q1 minus Q2 divided by C1 plus C2, which is equivalent to C2 into C1 V1 minus C2 V2 divided by C1 plus C2. So Q1 prime is the final charge of the first capacitor, Q2 prime is the final charge of the second capacitor. After distribution of charges, both the capacitor attains a common potential. Then during the distribution of charges in the conducting wire, certain amount of energy is dissipated in the form of heat in the conducting wire. Energy lost, which is equal to H is equal to half C1 C2 divided by C1 plus C2 of V1 minus one potential is taken as negative because both the capacitor is connected with the opposite polarity. One of the potential is taken as negative minus V2 whole square. Then energy lost, which is equal to half C1 C2 divided by C1 plus C2 V1 plus V2 whole square. This is another expression.